All right, so let's try first starting with our problem of the day. The problem of the day keys will be posted on the website within that course notebook as well, and I'll try to keep this updated as we go along. The problem of the day for yesterday I thought was a pretty unique one, and it segues into our next topic pretty nicely. So if you look at it, it looks to be a hydrobromination reaction. So let's redraw this out. And stop me if you have any questions or if it doesn't make sense. And we've got hydrobromic acid here. So the first step is the double bond will attack that proton and kick off bromide. And I had a lot of people ask me, well, how do we know which side that hydrogen goes onto? And this is a little bit of an interesting question. If you look at the top, I give you the product, so we know immediately that the carbocation must be at that position just based on our observed products. But let's take one closer look at this. If we've got this carbocation, we've got bromine nearby. This carbocation is a p orbital sticking directly up and down. So let me actually erase this a little bit, and I'm going to make this p orbital blue. So it's going up and down. That means that this bromine with its lone pairs is very attracted to that empty p orbital. So what will happen is this bromine will actually hop over into that p orbital, and it will form a new resonance form. And when you do that, you get bromine added on one side, and now this bromine has the positive charge. So some people actually caught this, and they noticed that, hey, this looks really similar to what we covered in lab with our bromination reaction. And if you have this, you can have it react with bromine using either one of these resonance forms. It doesn't really matter because we know that they're both adequate for explaining what's going on. If it's the one on the right, the bromine can only attack from the bottom side of the bromonium ion. So it will attack here, slingshot open that bromine, or it can just attack the open empty face of that p orbital. It has a much, much harder time attacking from that top face because that bromine is actually sticking up. So you run into this problem where sterically that bromide ion has a much harder time approaching from that top face rather than the bottom face. So in either case, you only get the trans product, not the cis product. And we'll talk a lot more about this bromonium ion and some of its relatives further on in this chapter. We may even get to some of those today. But it was kind of a unique problem of the day. Some of you may need to use your model kits to see some of these three-dimensionally, and that can help quite a bit. Yep?
So it doesn't have anything to do with steric clashes?
It does. So if you look at the one on the left, this resonance form, we're looking at steric hindrance, right? If we're looking at the one on the right, it's just the only option is that backside attack. So either explanation would be perfectly fine. At this point, we haven't covered the bromonium ion, so my guess is most people will talk about that steric clash, and that's perfectly fine with me. I just wanted to get you guys thinking three-dimensionally a little bit more. All right, so now let's go back to our acid catalyzed hydration problems. So if you remember yesterday, we talked about this acid catalyzed hydration where we had our double bond reacting with water in the presence of our trace amount of our catalyst, which is our acid. And we're able to install an alcohol at the more substituted position on the double bond. And we said the first step was the protonation of our water to form hydronium. Our second step is that double bond attacking our hydronium ion. And then we have water attack our carbocation, and it can attack from either the top face of the carbocation or bottom face. And then the last step, we've got to do our deprotonation, and in that step, we regenerate our catalyst. So we don't need a full stoichiometric amount of our acid in order for this reaction to go. However, there were a few other points I wanted to get to, so let's add those in. The first point is that this is really similar to hydrohalogenation. So very similar to hydrohalogenation. But with alcohols. In this example that I showed above, we used water. The reality is we could use any alcohol. Water is just the most common alcohol that you see for these reactions. So it's very, very similar. The acid that's used is catalytic. That means that we don't need a stoichiometric amount because we regenerate it during the course of the reaction. We only need a substoichiometric amount. The next one that is a little weird to think about, but somewhat intuitive, is that the reaction proceeds faster for more substituted alkenes. Why is that? Why would this reaction shown here go faster with a more substituted alkene? We only have a mono-substituted alkene shown here.
Because the cation form could be formed like a more stable cation.
Exactly. So the more substituted alkene that you have, the more substituted your carbocation will be, which means that it's much more stable. So we can actually run these experimentally and see that the rate of the reaction is much, much faster for tri-substituted than di-substituted than mono-substituted. So you can actually study these reactions based on their substitution patterns. The other thing to really watch out for these reactions is stereochemistry and rearrangements. So watch out for stereochem and rearrangements. So if we look back up here, we've got a secondary carbocation. If we had a group nearby that could stabilize it and form a tertiary carbocation, that will likely occur. And if there's a potential for forming stereoisomers, we would also observe those as well. In this case, the example I've shown, we don't have to worry about that. But quite often, these will rearrange. The neat thing with this reaction is that we can try to favor the addition over the elimination reaction a few different ways. So how do we favor addition versus elimination? What was the one we talked about yesterday? Temperature, right? Which temperature favors addition reactions, high or low?
Low.
Typically lower temperatures. So lower favors addition. The other one that's a little different to think about is acid concentration. And a weird way of thinking about this is we're not really concerned with the acid concentration, but more the water concentration. And I'll explain what I mean by that in a second. So let's take a look at the example we did in lab. If we have cyclohexene and we're trying to react it with water, and we've got dilute acid, so dilute catalytic acid, we can drive formation of cyclohexanol. However, if we do this same reaction going from cyclohexanol and we want to go to cyclohexene, we want to use concentrated acid, right? So we'll say concentrated H+. And we said we want to do this one under high heat as well. So the question is, why does acid concentration matter, or why does water concentration matter? Does anybody have an idea? Yeah, Le Chatelier's principle. I'm drawing these as one-way reaction arrows, but they're actually in equilibrium. And Le Chatelier said if we add more water to this reaction mixture, it's going to be pushed to the right. If we have less water, it's going to favor going to the left side. So using Le Chatelier's principle, we can actually try to drive this reaction towards elimination or addition. So if we're trying to do the addition reaction, we normally want dilute acid, which means we want a fair amount of water around. That favors formation of the alcohol over the alkene. And that is Le Chatelier's, if I can spell it right. Oh, did I spell it right? Le Chatelier's principle. All right, for those of you that want a really interesting example of this problem, I saw a good one in the book, and I'll let you guys work on it tonight if you want, and you can stop by my office or talk to me tomorrow about it. But let's take this alkene. Treat it with dilute acid. And when we do this, we get a very strange looking product. If you can, try to work through this reaction tonight, and remember that these acid catalyzed hydrations work with any sort of alcohol. So in this case, the alcohol is actually a part of the parent molecule, and it's going to close up and form a ring on itself. And see if you can do that entire mechanism at home. It's a little bit challenging, but it's a, I think, pretty interesting challenge to see how useful this reaction mechanism can be. All right, are there any questions on the acid catalyzed hydration reactions? No? Looks like a few people are copying this down still, so I'll wait a second. And this will be up on the website too if you guys need help with this, and I can post the answer here as well. All right, let's add another page here. The next reaction we're going to use is very similar to acid catalyzed hydration, but it's called Oxymercuration Demurcuration. Excuse me. There's a problem with acid catalyzed hydration that is observed very regularly, and I'll show you guys what this problem is. If we take something like water and we try to react it with this alkene using our acid catalyzed hydration conditions where we have dilute catalytic acid, we would want to naturally draw the alcohol adding to the more substituted position, right? But the reality is that we get another product as well. Why do we also get this product on the right? Yeah, there's some sort of rearrangement going on. In this case, it's going to be a hydride shift, which forms a tertiary carbocation. So in this case, you get two products. You get one normal product, and you get a rearranged product. That's a good question. The question was, is one favored over the other? That's very, very hard to predict. Most of the time, the rearrangement to a tertiary carbocation is favored, and so those tend to predominate. All right, so the problem with these reactions, it is very hard to control rearrangements. And this is a significant problem because if our target molecule is this one on the left and we're getting a significant amount of the one on the right, we're not being very efficient as chemists. So we need to figure out a different mechanism or different method of making the alcohol so that only the one on the left could be produced and not the one on the right. And the solution is admittedly a pretty dirty solution, but a very efficient solution. And it involves the use of mercury. So the solution is use mercury. So mercury is a pretty nasty, potent neurotoxin and terrible for the environment, but as long as we dispose of the waste correctly and handle it safely in lab, it's not that bad. So there's a few different steps for this reaction. So we'll do step one. Step one is we start out with this organometallic reagent. So mercury is divalent. It can bond to two different things. And this mercury is actually in equilibrium where one of these acetate groups will pop off. And if we do that, we've now got mercury with a lone pair and a formal positive charge, plus our acetate anion. So let's write down the names of these. We've got mercuric acetate, and oftentimes in your book, instead of drawing out the full structure, they'll just abbreviate it. So they'll write HGOAC2 for mercuric acetate. And over here we've got our mercuric cation. This is often abbreviated Hg plus OAC. And then the acetate anion over here is generally just abbreviated OAC minus. So the first step is forming this mercuric cation, which is very, very reactive. All right, let's go to the second step for this reaction, step 2. In step 2, we can have our double bond act as a nucleophile, as always, but react with the mercuric cation. So I'll draw the mercuric cation over here. And I'm going to use the abbreviation just to make it a little bit easier to manage here. So first step is our nucleophile, our double bond, reacting with our electrophile, which is the mercury. It's got that positive charge, which makes it a very good electrophile. And when we do this, we see something similar to what we saw in the problem of the day, where we can have the mercury, so HgOAC, and have our positive charge over here. But we know that this mercury has lone pairs on it. These lone pairs are adjacent to an empty p orbital that has a positive charge. So these lone pairs can actually dump in, and we can get a resonance structure where now we've got mercury as a bridgehead, OAC, and now our mercury has that positive charge. Let me redraw this bond a bit differently. There we go. So now we've got our mercurinium ion. Ion. And this mercurinium ion is very, very reactive. So in step 3, we're going to react this with a nucleophile. Yeah, mercuric acetate is almost exclusively used for this reaction. It's very dirty, and hopefully we'll develop a better method for doing this that avoids heavy metals, but for right now, this is far and away the most effective method for this reaction. So now that we've got this mercurinium ion, I have a hard time saying that, I'm just going to draw one of the resonance structures. So we've got HgOAC, lone pair, positive charge. We can have this react with a nucleophile. Typically, these nucleophiles are things like alcohols, so they've got a hydrogen attached. In this case, our nucleophile can add in from either that top face or the bottom face of that carbocation. In this case, it actually prefers the bottom face because we know over here that it can react with itself, that mercury can slingshot over. So in this case, the top face is usually blocked. The bottom face is preferred due to that resonance structure. So let's take a look at our product that we get out of this. In this case, we get those two methyl groups pointed up, our nucleophile pointing down. This nucleophile has a positive charge. Got our HgOAC. And we're almost there. We're going to lose a proton. I'm not going to draw the proton transfer, but you can imagine if you're running this in an alcohol solvent, that alcohol will come around and deprotonate this nucleophile. It's got the positive charge. And when we do that, we're almost home. We've got this HgOAC and our nucleophile. And then last but not least, we've got step 4. Step 4, I'm not going to ask you guys to know the mechanism for. Step 4, we just need to remove this mercury group through a reduction reaction. So if we've got this nucleophile attached where we want it, we want to pop off this mercury. And the most common reductant that's used to remove that mercury group is sodium borohydride. So it's NaBH4. It's a nice source of hydride, so we're going to replace that mercury group with a hydride group. There we go. So the last step is reduction of that mercury and installation of a new hydrogen on there. So now we've got a nucleophile added to one side of the double bond, a hydrogen added to the other side. The nice thing about this reaction is that there are no rearrangements. So if we look back up at the top reaction where we wanted to install the alcohol at that more substituted side of the alkene, we ran into a problem where it was reacting at the other side. So this time we can actually get around that and get it to install in the correct position. Whoa. All right, so this looks really complicated, but let's kind of look at the net reactions, and we'll learn to develop just an intuition when we see these reagents, what the reactions will look like. Yeah. Of which one? Step 4, we're adding sodium borohydride. That's a strong reducing agent. And hydride we know is H-. This H- will replace this entire group.
And then what happens
To the mercury? We're not going to really get into that. The overall reaction is fairly complicated for this. But the key thing to remember is for this last step, we're reducing off that mercury and installing a hydride there.
Can you go up to step 3 and slide over just a little bit? Is there a positive charge on the mercury on your final step on step 3?
Did I forget something here?
Is there a positive charge?
Oh, there should not be a positive charge here. Sorry, that was my fault. There shouldn't be a positive charge on that mercury. Sorry about that. So let's take a look at the net overall reaction. So if we've got something like our alkene that we worked with here, it's 2 steps. First step is to react it with our mercuric acetate, OAC2. And then we react it with our nucleophile. And then the second step, in order to get that mercury group off, we've got to react it with NaBH4. And if we do this, we get a nucleophile added in, we get a hydrogen added in, and we don't observe any rearrangements. If we do this with water, which is the most common reaction for this, it looks almost identical. We've got HgOAC2. This time, instead of our generic nucleophile, we'll specify and say it's water. And then we react this with sodium borohydride. And now we can install an alcohol without the concern of any sort of rearrangement occurring. And this reaction is pretty nice for that. It's only used when people are generally worried about a rearrangement occurring. It's not a very green reaction, so if there is no rearrangement potential, people will stick with the acid catalyzed hydration, just because it's a much more environmentally friendly reaction. All right, the next reaction is a little bit complicated, so we're not going to go into detail on the mechanism. But the mechanism is posted online as a supplemental video lecture. The mechanism, I think, is like 12 steps long and a little overwhelming. So if you do want to watch the mechanism video, you're more than welcome to, especially if mechanisms explain the overall trend to you. But for right now, we're going to kind of do an annotated version of this reaction. Whoop. Here we go. So the next reaction is called hydroboration oxidation. Hydroboration oxidation is a pretty neat reaction because all of the additions we've seen so far followed the Markovnikov addition rules, right? We were always adding our nucleophile onto the more substituted side of an alkene. However, that's not always useful for us. Sometimes we need to get the alcohol added to the opposite side or the less substituted side of an alkene. So hydroboration oxidation is used for anti-Markovnikov addition reactions. Addition reactions, meaning we're going to add our nucleophile to the less substituted side. And like I said before, see the website for the mechanism. I will say that having done chemistry for quite a while, I still hate this mechanism because it's so steppy. You're welcome to work through it on your own. All right, the overall mechanism, or overall reaction, excuse me, is, let's say we've got this alkene. We're going to react it first with borane, which we said is a very good Lewis acid. And typically when you buy this, it's either with THF or diethyl ether. So you may see either in your textbook. Typically they use THF. It's used in order to stabilize borane because it's so reactive. It'll react with anything it can get a hold of. So the THF just stabilizes it. The next part is they react it with hydrogen peroxide and sodium hydroxide. And when we do this, we can get the alcohol installed on the less substituted side. So now we can observe anti-Markovnikov products. The reasoning behind this is interesting. We're not going to do the entire stepwise sequence, but the first step explains the regiochemistry that's occurring here. So why is the alcohol adding to one side and not the other? So let's take an example, a really simple alkene. And we're going to have this react with our borane, which we know is BH3. And when we do this, we know that boron has this empty p orbital. I don't have it shown here, but we've seen it quite a bit before. We know that borane is trigonal planar. Going straight up and down is that empty orbital. This pi bond is very attractive to that empty p orbital. So it will try to bond with that boron. And then at the same time, this hydride from boron will hop over to that adjacent carbon. And when we do this, we get a really crazy looking transition state that looks a little bit like a square. So this double bond's halfway broken. We're starting to form a new bond with a hydrogen because it's breaking from that borane. So we get this square transition state. So I'm going to go through and box it off with that double dagger to indicate that it's a transition state. And when all is said and done, the boron adds to the less substituted side. So the question is, why doesn't this boron flip around and add to the more substituted side? What do you guys think? We're essentially trying to fit these two pieces together in a very particular way. Boron's a lot bigger than hydrogen, right? So if boron has the choice of approaching from the less sterically hindered side, it will always choose that. It won't try to approach from the more hindered side. So in this case, the boron will always add to the less substituted side due to the steric interactions here.
Sorry, when you say less substituted,
So if we look at this alkene, we've got two different spots on it. We've got the more substituted side on the bottom, and then we've got the less substituted side on the top. That's a good question. So in this case, the borane will add to the less substituted side of the alkene due to sterics. Let me move this up a bit. And the result of this is that that borane ultimately gets replaced by an alcohol. So we're able to install an alcohol on the more substituted side. All right, there's some interesting stereochemistry that occurs with these reactions too. The regiochemistry just refers to which carbon it adds to, but it doesn't really look at which face of that carbon it's added to. So we need to do a little bit more investigation for this reaction. So let's take a look at the stereochemistry. And I think this can best be explained by looking at a few different examples. Let me move this down. Let's take a look at this alkene. It's a cyclohexene. And we're going to do hydroboration oxidation. So we've first got that BH3.THF. And then we've got hydrogen peroxide and sodium hydroxide. When we do this, we're going to only get syn addition. So let me actually draw this in a different color. So this hydrogen will add to the more substituted side, and this alcohol that adds will also be a wedge. We won't get a reaction where the hydrogen adds to the opposite side of the alcohol. However, we also get another product, right? As long as they're adding to the same side, we could also say, well, they could add from the bottom side. So if we do this, the hydrogen could add from the back side, and the alcohol could add from the back side. So the key feature with this reaction is we get syn addition of hydrogen and our alcohol. That means they always are added onto that same face. What's the relationship between these two products? I heard some people whispering it. Syn means they add from the same face. Anti means they add from opposite faces. So in this case, if we're looking at these as a pair of products, what would their relationship be? Are they diastereomers or enantiomers? Enantiomers, right? So oftentimes from these reactions we get enantiomers. I used to have a really hard time remembering when you get Markovnikov versus anti-Markovnikov products, and then one day it dawned on me that there's a really simple trick. So I'll write down the trick I used. The trick is that when peroxides are used in addition reactions, you get the anti-Markovnikov product. So if you remember from the hydroboration section, we said we can do hydroboration with a pure acid like hydrobromic acid, but if we add even trace peroxide, it will add in the anti-Markovnikov addition fashion, right? If we look at this reaction up here, we've all of a sudden added peroxide again. So that tends to be the trend. Anytime you see peroxides, so H2O2 or ROOR, anytime you've got that oxygen-oxygen bond, it tends to be involved in some sort of Markovnikov, anti-Markovnikov reaction. Excuse me. Does that make sense? These reactions are tricky. Make sure that you go through your sapling problems. Try to work through those. They are time-consuming, I know, but the more time you spend doing these, the more they'll stick in your head. I know they look really simple when you work on them once, but you have to see them literally dozens of times before they stick. So for the stereochemistry for the hydroboration oxidation, you always get syn addition.
Well, no, you said one was like an attack or a top attack, and one was like a bottom attack, like syn and anti.
Oh, so the difference between syn and anti?
Yeah.
That's a good question. So let's briefly reiterate difference between syn and anti. So if we look at this diol here, this would be a syn diol, right? Because those alcohols are on the same side. If we are thinking about an anti-diol, that means that the alcohols are on opposite sides. It's used for any substituents when we're comparing them. So if they're in opposite faces, we call them anti. So syn just means same, anti means opposite.
Why do we do that instead of like cis and
For addition reactions, it's just generally the term that's used. Yeah, I don't know why they switch between them. That's an interesting question, though. All right, so I think we've got enough time to start getting into the next topic, which I think is pretty cool because it's something we can relate to on a day-to-day basis. How many of you guys have heard about trans fats? Trans fats, yeah. They talk about it all the time on the news. It's becoming a pretty big issue in the health community. And this all started with chemists. So let's start our page on catalytic hydrogenation. So if we look at something like cyclohexene, we can react this with hydrogen gas, and we can use a catalyst like platinum or palladium. Usually it's palladium. And if you run this reaction using platinum or palladium as your catalyst, you can add hydrogens across a double bond. And again, these hydrogens will add syn. So in this case, we're going to note that we get a syn addition of hydrogen. And this is a really interesting thing because chemists have known about this reaction for quite a while, that you can react any sort of alkene with hydrogen under high temperatures and pressures and reduce that double bond down to a single bond. It's a very useful reaction. When it started becoming really popular was right around World War II. Does anybody know why? Not the hydrogen bomb. So in World War II, there was a worldwide shortage of butter. So, yeah, right? So there was a shortage of butter. If we think about butter, is that a saturated or unsaturated fat? It's usually unsaturated, right? So if we look at butter, it's typically a solid, right? So saturated fats are typically a solid, unsaturated fats are a liquid. And there was a really serious shortage of butter during World War II. And they thought, well, we've got plant-based fats that are typically, sorry, I'm flipping up the words in my head. Plant-based fats are typically unsaturated. Animal-based fats are typically saturated. So we needed to figure out how to convert between the two. How do we get from a plant-based fat, which has double bonds in it, to an animal-based mimic that has all single bonds? And that's where hydrogenation came in. So you can take an animal fat, where typically you have some sort of double bond. You can react this with hydrogen and palladium. 4, 5. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can completely hydrogenate these double bonds, and you can go from a fat that's a liquid to a solid. And this was very popular. They tried to push margarine a lot during World War II. The problem is if you completely hydrogenate a vegetable fat, the solid becomes almost unusable. It's like a brick. It's not useful for baking. It doesn't taste very good. So instead of completely hydrogenating it, what they did was partially hydrogenate it. They said, well, let's just get it halfway there. So we'll take this liquid oil, we'll try to turn half of it into the solid fat. The other half can be the liquid fat, and it will actually be a usable product. And that worked great, right? The problem is that with partial hydrogenation, you get a side reaction So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, where you go from the cis fat, and then the reaction doesn't occur completely, and you end up with some of the trans fat. It will actually isomerize to the trans form, and this trans fat, the more we've studied it, the more we realize that it is really, really bad for you. Even trace amounts of it lead to cardiovascular problems. And so they're trying to steer restaurants and consumers away from eating and making it. The reason that industries have had a hard time with this change is that partially hydrogenated oils are really useful. They don't go rancid very quickly. They last forever. I mean, my grandma, I think, has a thing of Crisco that she's had in her pantry for probably 40 years, right? If you had a thing of vegetable oil in your pantry, it would probably go rancid after maybe a year, right? So using these trans fats, or these partially hydrogenated oils, they last much, much longer, but they're really bad for you. And we're trying to figure out ways to partially hydrogenate oils that doesn't lead to these trans fats. We just have a very hard time doing that. Typically, we have to just substitute it using a different oil like palm oil. And so if you buy Crisco today, it typically has palm oil rather than partially hydrogenated vegetable oil. There's a link on the class website, too, if you're interested in reading about it more.
I just want to say about the palm oil.